Welcome to this explainer. I am absolutely thrilled you're here with me today because we are going to unpack the absolute bleeding edge of the robotics industry. I'm talking about things that honestly, even a couple of years ago felt like pure science fiction, but are literally happening right in front of us. From the mechanical marvels of robotic hands to the downright frantic arms race for AI data, we're going to take a structured look at exactly where hardware and software are colliding today.
Okay, let's dive right into this. What actually happens when robots leave the lab? For decades, right, these machines have been safely confined to highly controlled factory floors or super sterile research facilities. But today, they're stepping out into our messy, unpredictable world. How do they walk on uneven ground without wiping out? How do they avoid hurting us? How do they learn to fold laundry or, assemble a spaceship? We are bridging that gap between the lab and reality right now, and the solutions engineers are coming up with are absolutely going to blow your mind.
Here's our roadmap for today. First, we'll look at hardware, specifically hands and shoes. Then we'll check out the global humanoid race, followed by the robot safety crisis, the data collection gold rush, and finally we'll look at taking robots to space.
Section 1. Hardware, hands, and shoes.
And this brilliantly illustrates two completely different yet stunningly advanced approaches to robotic hands. Take Honda's new hand, for example. It's only got 3 interchangeable fingers and a thumb, but man, it is a powerhouse. Each finger can lift 15 newtons, that's about 5 kilograms or 11 pounds per finger. But it's not just strong, it's incredibly precise. It uses this fascinating optical sensor setup for touch. They are literally using fiber optic threads to carry light to a camera just to sense pressure. It gives it enough accuracy to autonomously thread a needle. Crazy, right? Now, contrast that with the Wuji hand. This thing is a mechanical masterpiece focused on direct-driven power using a highly specialized worm gear. It's totally back-drivable, which means it moves fluidly and naturally when you push against it, though, to be fair, right now it still requires an external wrist to function.
Now, with Boston Dynamics releasing their new fully electric Atlas robot, it brings up a really surprising question. Do robots need shoes? When we think of humanoids, we kind of just picture bare metal feet clanking on the pavement. But engineers are quickly realizing that foot design is way more complex than that.
Think about it. We humans wear shoes for warmth, for protection, to keep our feet secure. Robots obviously don't get cold. They don't need a laced-up sneaker. What they actually need are highly engineered, interchangeable soles. Why? Well, shock absorption, for one. Every single time a heavy robot takes a step, that vibration travels right up the leg and degrades the mechanical actuators. Plus, imagine if a robot steps on a random bolt on a factory floor with a rigid metal foot. It's going to slip, lose its balance, and crash. A compliant rubber-like sole absorbs that obstacle, keeping the whole machine stable. And honestly, we really don't want heavy metal robot feet completely tearing up expensive factory floors. It's a massive design challenge, especially since robots like Atlas are designed to walk backwards and forwards equally well, so they actually need a completely symmetrical foot.
Section 2. The global humanoid race.
So the current global landscape is really divided by some distinct cultural and economic drivers. Over in Japan, there's this deep, long-standing cultural acceptance of robotics. Seriously, a robot roaming around a shopping mall there barely turns a head. Because of that, they produce absolutely elite hardware, like that Honda hand we just looked at. But industry insiders do note that they're currently trying to catch up a bit on the modern software and AI side of things. Then you have China, where integration is just ubiquitous. In places like Shenzhen, you've got automated roadside delivery bots seamlessly dropping off packages to humanoids right at residential buildings. And the scale is staggering. There are reportedly up to 867 humanoid startups in China, all pushing for rapid deployment. Meanwhile, in the US, the focus is heavily geared toward reindustrialization. There's a massive, bipartisan push to onshore supply chains. So you see funding going to companies like Westmag to build American robot actuators, ensuring the industry doesn't rely entirely on overseas manufacturing.
Section 3. The robot safety crisis.
As one industry insider so bluntly put it, the amount of torque that you need to make this robot useful is very dangerous for a human. There is no e-stop on here. This tension was really highlighted recently when videos started emerging of underground robot boxing leagues, alongside heavy industrial bots operating right in public spaces. Here's the thing. These machines have to be strong enough to carry heavy loads. That means their motors produce enough torque to seriously injure a person. And shockingly, a lot of these early models lack a basic, reliable, wireless emergency stop, or e-stop.
So, the crucial point here is exactly how quickly things can go completely off the rails. Imagine this scenario, based on recent incidents. An operator using a remote controller accidentally triggers an unsafe preset motion, let's say a high kung fu kick. The heavy, high-torque robot instantly loses its balance and crashes to the ground, flailing its limbs wildly as its software desperately tries to correct the fall. And because there's no wireless kill switch, human engineers are forced to literally run up and physically grab this thrashing, highly powerful machine just to turn it off. It is a massive liability. The industry urgently needs built-in safety standards like millimeter-wave human detection sensors to force these robots to power down the absolute second a human enters their physical space.
Section 4, the data collection gold rush. Now, to understand this gold rush, we really have to understand teleoperation data. See, you can't just program a robot to fold a shirt. It doesn't work like that. You have to train its AI. To do that, a human wears a bunch of sensors or a VR headset and physically performs the task. The robot's AI then records all those human-guided physical actions and learns from them. This data, it is literally the lifeblood of the entire robotics industry right now.
And remember this number from earlier, 867? With up to 867 humanoid companies popping up in China alone, plus dozens of massive players over in the US and Europe, the sheer volume of data required to train all these different AI brains has triggered a totally chaotic, unregulated market. Everyone is fighting tooth and nail for the exact same resource. And this desperation is leading to what insiders are calling a cash incinerator. Companies are spending millions on raw data, and honestly, some of it is incredibly low quality. Get this, people are being paid thousands of dollars to clean New York apartments while wearing heavy mittens, bulky coats, and a neck brace. Why in the world would they do that? To simulate the physical limitations of a robot. But here's the catch. Because the human operator feels super clumsy and hesitant in all that gear, the data they record is clumsy and hesitant. When they feed this sort of drunken data into the AI, the robot ends up moving incredibly slowly and making a ton of mistakes. It's an absurd, incredibly expensive bottleneck that the whole industry is desperately scrabbling to fix.
Section 5, taking robots to space. Let's move to a completely different environment and see how this all builds up. When you remove Earth's gravity, the entire form factor of a robot fundamentally changes. Take a look at the Astrobee robots that are currently being tested on the International Space Station. Because of their microgravity design, they don't need heavy legs or feet. Instead, they use what are called quadrupus grippers. Basically, 4 tentacles designed exclusively to grab onto handholds and heavy cargo floating around the station. And to move around, they just use simple, low-powered ducted fans to puff air and glide right through the ISS. They are incredibly efficient machines built for very, very specific environment. Now, what's really fascinating here is the underlying philosophy behind why we're building these robots in the first place, whether they're down here on Earth or up in space. It really comes down to the difference between toil and labor. Toil consists of those exhausting, degrading, repetitive tasks, like a farmer manually harvesting crops under a blazing sun, or an astronaut spending hours just unloading a resupply cargo ship. Labor, on the other hand, is fulfilling, highly valuable work, like a carpenter crafting a beautiful piece of furniture, or that same astronaut running cutting-edge scientific experiments on the ISS. Ultimately, robots exist to eliminate toil, completely freeing us humans up to focus our time and our energy on meaningful labor. Which brings us to our final thought. Are we really prepared for this robotic future? We've seen hands that can thread tiny needles, mechanical souls custom-built for factory floors, the literal physical dangers of untested software, and robots specifically built to float among the stars. The transition from science fiction to our living rooms and our workplaces, it's happening right now, fueled by a massive global race and absolute mountains of data. It is going to fundamentally reshape how we work, how we live, and how we define human labor. Thank you so much for joining me for this explainer today. Keep your eyes open because the future, it's already here.